All right, so now that we have the basics under our belt, let's run a real population model. This time we're going to run a model for the Yellowstone grizzly bear population. We are going to use real data. This is a model that could actually have real world relevance because it is based on real data, and we are doing our best to make this model as realistic as possible. And what we're going to try to do with this model, we're going to try to better understand the future of the grizzly bear population in Yellowstone Park and the processes that might regulate this population. Now, in this case, we're not going to run any management or conservation scenarios. Instead, we just want to get a better handle on what the future might look like for this population. In addition, we want to know how many individuals this area in Yellowstone Park can support. We want to know the carrying capacity of Yellowstone. Knowing the carrying capacity and knowing the expected future abundance is really important for managers to understand how to manage the population, what's the target abundance, and above that target you might consider actions like culling or increasing the hunting rate. So let's walk through the steps in building this model. We're not going to build it from scratch because that's asking a little bit too much, but let's go through this together. Now, this first step in building any population model is to just conceptualize how this population works. How many life stages are there? What's the age at maturity? Potentially, what is the senescence process? Like, what's the oldest possible individual? We're not going to include that here, but that's something you might consider. So what we do is build a diagram that looks something like this. Now this, as you probably already have worked with Insight Maker a little bit, you can tell this is from Insight Maker. But the point is that we can see that we have decided based on the literature, we've done a literature review, and we've figured out that there are 4 main stages in the grizzly bear's life history, and we're going to divide it up into a cub stage, yearling stage, which is the first year of life, individuals in that first year, subadult, and adult. And the adult stage is the only reproductive stage, so subadults are non-reproductive. And the subadult stage lasts approximately 3 years in grizzly bears. So that is the 3rd, 4th, and 5th year of life you can consider as being subadult stage. So it looks something like this. We can see that cubs transition to yearlings, yearlings transition to subadult in their 1st year, so that would be in their 3rd year of life. And the second subadult stage is in the 4th year of life, 3rd subadult stage is in the 5th year of life, and then they become reproductive adults after that. And only those reproductive adults are capable of contributing new offspring into the population. And there's a certain survival rate that's going to be associated with cubs, yearlings, subadults, adults. And so it's a fairly simple model, but also fairly realistic. So that's the first step, is just to conceptualize the life history. Now the next step is to parameterize the model. And to do that, we're going to need to do a literature review. So what we did is I've pulled out a table for you from the literature. This is from a study, Schwartz et al., 2006. And this study documents the vital rates for this population, and it is really right along the lines of the conceptual life history that we've already put together. We have cubs, yearlings, subadults, adults, and the fecundity, and the adults are the only stage that can produce offspring. Here we see the survival estimates for the cub stage, where the estimate is 0.64. And I should mention that what we see here in this table, there's actually 2 estimates for each of these vital rates. One represents the period from 1983 to 2001, and the other represents a more recent period from 2002 all the way to 2011. So we have two vital rates or two estimates for each vital rate, one for an earlier period and one for a later period. And we'll talk more about that later. But let's focus on this first period for now. So to keep things simple, the cub survival, let's say, is 0.64. Yearling survival is 0.817 or 81.7%. Subadult survival is 95%. Adult survival is 95%. Now, why did I say adult survival is 95%? Well, we don't really care about males. So this whole line here of males, let's just not even think about that, because in population ecology, males really do not matter. We don't generally even model the males. We model the female population only, and these are called female-only models, and probably 80% or more of the population models you'll see out there are really female-only models. We don't care about males. Why do we not care about males? Well, really, how many males are needed? Males obviously don't produce offspring. So how many males are needed to fertilize all the females? Well, usually in most animal populations, most wild populations, not that many. Just a few males are needed to fertilize all the females, essentially, which means that the number of males in the population doesn't really matter. Even if there's a few males, that all the females will be able to reproduce, and the males aren't going to actually produce any offspring. So we don't really care about males. Males are unimportant to population models. All right, so we're going to ignore that. So female adult survival is 95%, and the fecundity is 0.362, or for each female in the population, we can expect that she will produce 0.362 offspring into the next year, So here's our basic data. We also need, of course, in addition to survival rates, we need to know the abundance. We need to know how many individuals are out there. All right. And so from the same paper now, we know that adult females represent approximately half the total, reproductive females represent approximately half the total female population. That is, so the rest would be in subadult or juvenile classes. So about half the total population is in the adult stage, and total abundance, we know approximately the total abundance in the greater Yellowstone Park area. And that if we look at this figure here, all we have to do is add up the triangles and the squares here to get the total abundance, because the triangles represent those counts inside Yellowstone National Park, and the squares represent counts of reproductive females in the greater Yellowstone area. That is this area outside Yellowstone Park, but adjoining or next to Yellowstone Park. So if you add up the two, you get all the reproductive female bears in and around Yellowstone Park, and that's the area that we're interested in. So just think about adding those two together for every year, and that gets an estimate of abundance. And so 1983, you can see the abundance was approximately 12, 13 or something like that. And then by 2001, 2002, 2003, the abundance was more like just over, 30, about 50 or 60 or something like that, total in the greater Yellowstone area. All right. So let's just take 1983 for now, and let's initialize our population to 1983 abundances. Now, before we can actually do anything, we have to now get our model. So scroll up to where it says you can clone the base Grizzly Bear model here, and let's move over to Insight Maker. So click on this link, and we are going to slide over into Insight Maker and parameterize this model. So do click on that link, and the link should look something like this. So you should see a grizzly bear model, and just note that the model is not parameterized yet. So basically this is the initial abundance of cubs, initial abundance of yearlings, and cub survival, yearling survival. So all these things I just set at 0 so that you can have a chance to put the actual parameter values and initial abundances in this model. So that's your job. Let's go back to the lecture for a second and just go over what we need to do. So here are the initial abundances that we're going to use. We're going to have 3 cubs, 3 yearlings, 2 in each of the subadult stages, subadult 1, subadult 2, and subadult 3. And then we'll use 10 adults. And that's just based on this figure here and the fact that this represents about half the total population. So we'll have 10 adults essentially right here, 10 adults, and then we'll have about 10 of everyone else, and then we'll just like add up. We'll just divide them up in a reasonable way. So we have 3 plus 3 plus 2 plus 2 plus 2. It's a little more than 10, but close. So that is just a guess at how the individuals were distributed back in 1983, and so we can use that as our initial abundances. Use the table to define the vital rates. So define cub survival is 64%, so on and so forth. So let's move over into the Insight Maker model. And when we do parameterize the model, we'll put all the parameters in. We can simulate, and we just hit the run button, and we're going to just check to see if what it looks like. And then I have a quick short answer question for you. So let's do that. First of all, pause the video and take a few minutes to parameterize the model. So change these zeros into the values that they should be, and hit simulate and just see what the model looks like, and make sure you understand what's going on. Take your time with it and come back to the video when you are ready. All right, so your parameterized model should look something like this. Now you should have 3 cubs, 3 yearlings, that's the initial abundances, 2 subadults in each of the subadult stage 1, 2, and 3, and then follow the table to define your vital rates, the cub survival rate, the yearling survival rate, so on and so forth. So it should look something like this, and when you simulate it, you'll see that the results are a little random. So every time you simulate it, it'll look a little different. And so you can't really interpret just one model run as being the truth about the future for this population. So the first thing you might want to do is, here's the total abundance. You have 2 different views here. You could either look at the total abundance over time or the age-structured total abundance over time. This is the adults, yearlings, subadults, and and cubs somewhere in there. So there we go. So since we can't interpret a single run as being the truth, what we can do is run a whole lot of runs and look at the cloud. So we use the sensitivity testing tool to run, let's say, 50 runs here. We're going to monitor the adult age class, or we could monitor, let's monitor the adults for now. Monitor the adult age class. Let's looks good. Let's run it. There we go. So now we can see the results from multiple runs, and now we get a better idea of not only what the future might look like for this grizzly bear population, at least over the next 20 years in this case, but also the uncertainty we have about this grizzly bear population over there. So there's quite a bit of uncertainty in this case. The population might be almost 70 after 20 years in this case, or it might be down to 30 or something like that. So it's a growing population, as you can see, but there's a lot of uncertainty. So the first thing to think about is this model realistic? Does it make sense based on what we actually know, because basically the year zero in this case represents 1983. That's the initial year that we have data for. 1983, we know there were approximately 10 adults around in the Yellowstone population, reproductive adults, females. So that's realistic. Obviously, we set it to be realistic. But then 20 years later, in 2001, 2003, I think we have information that there was approximately, 50 or so total individuals in the population. We can look at that from this figure here. We can count up the total number that were, in the park proper and in the general area, add those up, and we get something like, 55 or so. Is that realistic that 20 years later there were 55 females in the greater Yellowstone area? Well, let's look at that. Where's 55? It's about here. It's not bad. There could easily be 55. It's within the realm of possibility that there could be 55. So this is realistic in the sense that this model produces something that looks like what actually happened. So that's called validation for a model. We can test the predictions of the model against real data and figure out if the model is doing something that is totally unrealistic, or ideally something that looks realistic. All right, so far so good. We feel good about our model being realistic. Now try changing the settings and run the model for 100 years. All right. And now rerun the sensitivity testing tool, all right, and look at the results. And what I'd like you to do now is to go back to the lecture and go to Web Campus, actually, and answer the following question. Where are we? Short answer question number 1. Based on this 100-year simulation, do you think this model of the Yellowstone grizzly population is biologically realistic? Why or why not? So take a minute, pause this video, run the model, and go into Web Campus and answer the question. And then when you're ready, return to the video. All right, so let's add one more process to this model now. And this process is going to be called, or it's often called, density dependence. And that means that as populations get bigger, oftentimes individuals start competing with one another for resources. And by competing for resources, each individual does not get as much of the pie, basically not as much resources. And that lowers their chance of survival, and it lowers their reproductive rate. So the vital rates themselves, like potentially cub survival, yearling survival, adult survival, fecundity, all of these vital rates can change as populations get bigger, because each individual is less healthy, essentially, because they're competing with each other for food and other resources. So let's look more closely at this table, because this table represents initially a period where there was low abundance in the population. So the population was low abundance back in 1983 during this period where these vital rates represent. These vital rates represent this early period where the population was low abundance. And these vital rates here, this 0.553, 0.539, these vital rates represent or estimates from a period where the grizzly bear population had a chance to grow. And so the population was bigger. And if you look at these vital rates, you can start comparing between, okay, cub survival during this early period was 64%, but during the later period, cub survival dropped to 0.553. So there was a drop in survival, which you might expect when the population gets bigger and individuals are starting to compete with one another for resources. So just take a minute to look over this table and look at the differences between the vital rates before during the early period where there was low abundance, and then after, during this period when there was higher abundances and potentially competition. So take a minute to look that over. What do you notice? All right. And which vital rates changed the most from 1983 to 2002, from this early period to this later period? Pause the video and answer the short answer question in Web Campus. Which vital rates changed the most from 1983 to 2002? And also, what processes might cause this change? Can you think of any reason for this change? Why might the vital rates have changed the way they did? All right, so please pause and answer the question, and I will be right back. So you probably noticed that a lot of the vital rates changed from the earlier period to the later period. But one vital rate changed a lot more than the others. Particularly, yearling survival changed from 81.7% in the earlier period with low densities, and it changed to 53.9% with higher densities. And that is a very significant change. Now, we can imagine that this change is due to competition, lack of resources. Maybe the yearlings compete with older individuals for resources and are just unable to compete very well when the population gets large and they are unable to survive. Many of them die because they're not able to get resources. So let's include this process in our Insight Maker model. This is a realistic process and one that probably, now that we have some data, we need to include this process in our model in order to make our model more realistic and representative of what's really going on. So first of all, I want you to make sure that you parameterize the model so that we're representing the later period with higher densities. So we're going to have higher abundances of cubs, yearlings, subadults. Let's have 40 adults. We're going to try to represent that image we saw earlier of this population. We're going to try to use this figure here to initialize the population more like it was in something like 2003. So that's what we're doing here. We'll have 15 cubs, 15 yearlings, 5 subadults of each stage, and then 40 adults. So that's how we'll break it down. In addition, we'll use the table values for 2002 to 2011 to define the vital rate. So cub survival now is 55.3%. Yearling survival I'll skip over for a second because we're going to make that a density-dependent process. Subadult survival should be 94.8%, adult survival 94.8%, and fecundity 0.336. All right, so those are the values we'll use. But in addition, what we'd like to do is make this yearling survival value density dependent. So it's going to change as the population density, the total abundance goes up. Now we see this link here between abundance and yearling survival. So there's going to be an equation in this yearling survival variable that defines how yearling survival is going to drop off with increasing densities. And in the lecture website, I have a description about how we generate this equation, but I'm not going to go through it now. Just know that we're using the available information about what yearling survival was in the 1983 to 2001 period, which was 81.7%. And then we see that it dropped off to 53.9% as the abundance went up. So we're using that information to define a linear model or a linear equation that relates yearling survival to total abundance. So we can enter that equation just by clicking the equation editor, which is that equals sign. When you move your cursor over that yearling survival, you see that equals sign. Just click on that to open up the equation editor. And now we can type in the following equation. This is the equation that relates yearling survival to total abundance. It's going to be 0.864, that's the intercept, minus 0.0047 times total abundance. And we can just click on total abundance to complete this equation. So now the Insight Maker will recompute yearling survival every year on the basis of what the total abundance was. And as the abundance gets bigger, yearling survival will get smaller. And that's realistic because we have data to support this relationship. So take a minute to put that equation in. When you're ready, hit apply. And now we've defined yearling survival as a function of total abundance, or total female abundance, we should say. And we've defined all the other variables based on the observed estimated survival rates and fecundities. And so we're ready to run the model. So we can simulate from this model. And there we go. We see and notice that I've now changed the settings so that the simulation length is now 100 years. So it runs for a whole 100 years. And every run's going to look a little different. So what do we do when every run looks a little different? Well, we have to run lots and lots of simulations, and we can use the sensitivity testing tool to do that. And we can run 50 or 100 replicates and monitor that. This time we're monitoring the total abundance, not the total adults, but the total abundance. And we'll run this analysis and see what happens. And so there we go. We have a density-dependent model that is probably a lot more realistic than the model we had before. As you might have noted, the model before was not super realistic when we ran it for 100 years. All right, so now we have this model. Let's go back to the lecture. Where were we? So we've defined this formula for yearling survival. And now it is your turn to work and answer the last two questions on your own. So again, you can clone the model here. Now, set the parameters, make sure the initial abundances are set at the values for 1983 to 2001. So you're going to go make sure you have this density-dependent model. You can, if you want, you can clone the full density-dependent model. Here, you don't have to use your own model. You can use the model that I've already developed to make sure you're using the right model, and make sure the initial abundances are set at the values for 1983 to 2001, and the model is set to run for 100 years. So remember, in 1983 to 2001, the initial abundances were 3 cubs, 3 yearlings, so on and so forth. So just make sure that you're using those initial abundances to answer this question. All right, and the model's set to run for 100 years. So what I want you to do is to run the model with and without density dependence, and I'll show you a trick for doing that. What you can do is what's called comment out the density dependence, so you can just go back and forth between the density dependent model and the density independent model, and this is how you can do it. Use the hashtag or £, and that will basically make Insight Maker ignore that whole line, and instead you can make the model density independent by typing in 0.539 here, and that was the value of yearling survival during the higher density period, and so we can run it that way. There we go, and that would run a density independent model, and you can see that model ends up getting really high values. Total abundance near 600 in this case, this random run that I just ran. So you can go back and forth between the density dependent and the density independent model this way. All right. Let's go back here and finish going through the assignment. So we can just go back and forth, run the model with and without density dependence, and answer the following questions. First of all, what's the new carrying capacity? What's the carrying capacity of the grizzly bear population in Yellowstone Park? And you're going to want to use the sensitivity testing tool to do this. But this is a really important question. And what we've done is we've used data and we've used our model to try to understand how many grizzly bears this area can support. And that's a tremendously important question for managers to know. And it's also an emergent property of our new model. We did not impose a carrying capacity on our model. We just used the data to define how yearling survival is related to density, and we ran the model, and carrying capacity emerged from that. And so that is another really useful thing. This is something that makes models so valuable in ecology and conservation, is because when we run them, we can get important and often unexpected results from our models. And when those results can have incredible importance for basic science and for conservation. Okay, so what's the first short answer question? What's carrying capacity at Yellowstone? And the final short answer question is, when you run the model with and without density dependence. So in one case, you have the density dependent, the equation that relates yearling survival to density. And in the other case, yearling survival is constant and it's assigned the value 0.539. In each case, what's the approximate 90% confidence interval for the total population abundance after 100 years? And to do that, we can use the sensitivity testing tool. Remember, the sensitivity testing tool gives you something that looks like this. It gives you these regions. So now take the 90% region, right? And the 90% region here goes from approximately 1 to approximately just over 110. So that would represent the final abundance after 50 years. The 90% confidence bounds, that represents your uncertainty about the future abundance, would be from 1 to 110. That would represent your uncertainty. In this case, what do you get for that 90% confidence interval that represents your uncertainty about the population 100 years in the future, the final abundance of the population 100 years in the future? So that's your final short answer question for the grizzly bear exercise. Good luck, have fun, and please add any questions you have in the discussion board. And otherwise, I will see you in the next lecture, which is on the loggerhead sea turtle PVA.